Welcome to the deep dive. We unpack complex topics, giving you the essential insights and maybe some surprising facts you need to be truly well informed. Today, we're diving deep into something really critical for engineers and MEP professionals, mechanical, electrical, plumbing folks. We're talking about the unseen power, really, of hydraulic calculations in water-based fire protection systems.
Yeah, and these aren't just, numbers on a page. They're not abstract concepts. They are the fundamental force that dictates whether a fire protection system actually does its life-saving job
Yeah.
or if it tragically fails under pressure. It
Yeah.
really comes down to precision, safety, and making sure everything lines up with standards like NFPA 13.
Okay, so let's get into it. Let's unpack this really crucial topic and understand why these calculations are the absolute bedrock of reliable fire safety for every building.
Sure.
So when we say hydraulic calculations in fire systems, what are we actually defining? What's the core idea here?
Okay, at its heart, a hydraulic calculation, in this context anyway, is the process. It's a precise process. You're determining the exact water flow and pressure needed, throughout the entire fire protection system. The whole point is to ensure it can effectively control or maybe even suppress a fire in a specific hazard area. Think of it like a detailed plan for the water. You're proving the system can meet the specific hydraulic demand for that particular hazard.
Right, so it's about making sure you get the right amount of water
Exactly.
with the right pressure, exactly where it needs to go when a fire breaks out.
Precise. We're talking about guaranteeing adequate water delivery. All the way from the source could be the city main, a tank, maybe a fire pump,
Right.
all the way to the furthest sprinkler head, or maybe the one that's hardest to get water to, the most demanding one. And this means considering every single piece of pipe, every elbow, T, valve, even how much the pipe goes up or down, elevation changes. And our main guide for all this, our sort of rule book, is NFPA 13. That's the standard for the installation of sprinkler systems. It's really the Bible for this stuff.
That sounds incredibly detailed. I mean, honestly, like a huge amount of work. So why can't we just, make a good guess? Or maybe just massively over-engineer the system to be safe? What's really on the line if these calculations get skipped or, maybe worse, done wrong?
The stakes are incredibly high. The consequences can be just catastrophic. Without accurate calculations, you're facing major risks. The biggest one, outright system failure. An improperly designed system, it just might not deliver the water volume or the pressure needed to put out a fire. That leads to a total devastating failure right when you need it most, in an emergency.
And when a system fails, we're not just talking property damage, are we? That's not the main concern.
Oh, absolutely not. It directly impacts life safety. That's paramount. If the water doesn't hit the fire with enough force or enough volume, the system might not prevent flashover, that terrifying point where a whole room just erupts in flames because of the heat buildup, or it might not wet surfaces enough to control the fire spread or even keep escape routes usable for people trying to get out, like UL 1626 aims for in homes. These systems are primarily about saving lives. If they fail because the water calculation was off, people are in serious danger.
Okay, so life safety is number one. What about the regulatory side? There must be big compliance issues too.
You hit a really key point there. Code compliance is critical. Fire protection systems have to comply with nationally recognized standards. It's not optional. It's a legal requirement, an ethical one too. Plans, they have to be submitted, reviewed by the AHJ, that's the authority having jurisdiction, and detailed calculations. They're a non-negotiable part of that review. Errors here. They can get your plan stamped, rejected, and resubmit. That means costly delays, lots of rework. It can jeopardize the whole project schedule, the budget. We're talking strict adherence to NFPA 13, yes, but also related standards. NFPA 14 for standpipes, NFPA 20 for fire pumps, 22 for tanks, 24 for private fire mains. These aren't just suggestions. They're the rules we have to follow to keep people safe.
And I've heard about this cold soldering effect. It sounds kind of counterintuitive. What is that exactly? How do good calculations stop that?
Ah, yes. That's a really crucial detail. It really shows the kind of precision we need. So if sprinklers are too close together, or maybe the system pressure is just a bit too low, the water spray from the first head that opens can actually cool down the nearby heads that haven't opened yet. This cold soldering stops those adjacent sprinklers from activating. Even if the fire's right there moving towards them, it creates this blind spot, a shadow in the protection pattern. It delays the whole suppression effort, lets the fire grow in that cold zone. Accurate calculations make sure the spacing is right, you pick the right K factor for the heads, and you have enough pressure. That avoids this specific kind of insidious failure. It makes sure every head opens when it's supposed to.
Okay, the stakes are clearly massive. So let's maybe pull back the curtain a bit. How do engineers actually get this right? What are the core formulas, the principles they use?
Right. Let's get into the nuts and bolts. At the heart of how any sprinkler performs, there's this fundamental formula. It's like it's DNA. Q equals K times the square root of P. So Q, that's the flow, usually gallons per minute, GPM, how much water comes out. K is the sprinkler's K factor. Think of it like its efficiency rating, its discharge coefficient. It's specific to each head type set by the manufacturer, really important. And P is the pressure, but specifically the flowing pressure in DSI right at the sprinkler head itself while water is actually spraying out.
Got it. So Q equals K, KP. And if you know two of those,
You can always find the third. Exactly. You can rearrange it. If you need the K factor, maybe for testing, it's K equals Q divided by the square root of P. Or if you get into the minimum pressure required for a certain flow, it's P equals Q divided by K, that whole thing squared. So for example, a really common sprinkler, K factor 5.6, if it needs to flow at, say, 7.0 PSI flowing pressure, you can calculate exactly how much water that is. The simple-looking formula. It's foundational. It links the water supply directly to what the sprinkler actually does.
Okay, so that handles the sprinkler itself, but like you said, the water has to get there. Through potentially hundreds of feet of pipe, twists, turns. How do you factor all that in?
Ah, yes. That's where the real engineering kicks in. That's the bulk of the calculation, really. Beyond the sprinkler, we have to meticulously track how pressure changes through the whole pipe network. The first big thing is pressure loss due to friction. Water moving through pipes, it rubs against the walls. That friction fights the flow, makes you lose pressure, reduces efficiency. We mostly use the Hayes and Williams equation for this. It looks a bit scary, but FL equals 4.52 times Q to the power of 1.85, all divided by C to the power of 1.85 times D to the power of 4.87.
Whoa, okay. That is a mouthful. Can you break down those variables a bit?
Sure, sure. So FL is the friction head loss. It tells you how much pressure you lose for every foot of pipe, usually in feet of water per foot of pipe, which we then convert to PSI. C is the Hayes and Williams roughness constant. This number reflects how rough the inside of the pipe is. So like 120 is typical for new Schedule 40 steel wet pipe, but an old corroded pipe, maybe its C values down to 100 or 90 or even less, that means way more friction. Choosing the right C is critical. Q is the flow rate, GPM, in that specific piece of pipe. And D is the inside hydraulic diameter of the pipe, not the nominal size, the actual inside diameter.
Okay. And what about all those fittings, the elbows, T's, valves you mentioned? They add friction too?
Oh, absolutely. And that's a critical point people sometimes underestimate. You have to account for the pressure loss from fittings. T's, elbows, check valves, control valves, they don't just change the water's direction. They create turbulence. They restrict the flow. So what we do is we convert their resistance into equivalent pipe lengths. For instance, a 1-inch standard T might add the same friction loss as, say, 4 extra feet of straight 1-inch pipe. A 1-inch elbow might be like 3 feet. You add up all these equivalent lengths, even small fittings can add up to significant pressure drops across a whole system. It's crucial.
Right, that makes total sense. Okay, friction loss, check. What about buildings with multiple floors? Water going up must lose pressure, right?
Excellent point. That's our second major factor. Pressure change due to elevation. Just gravity at work, water moving up or down. It gains or loses pressure. Simple as that. The rate is 0.433 psi for every foot of elevation change. So push water up 10 feet, you lose 4.33 psi, just fighting gravity, let it flow down 10 feet. You gain 4.33 psi. Gravity helps you. Ignoring even, relatively small elevation changes in a big building, that can throw your final pressure calculations way off.
Okay, friction, elevation. And then sometimes the city water pressure just isn't enough to handle all that loss, plus the sprinkler demand. That's where pumps come in.
That's exactly right. This is the third major piece we often deal with. When the water supply coming in, maybe from the city main, just doesn't have enough pressure to meet the total demand of the system, that's when we install fire pumps. Their job is to boost the pressure. It's really important to remember, though, pumps add pressure. They don't create water. The flow has to be available from the source. The required pump pressure basically is the sum of everything. It's the pressure needed at that most demanding sprinkler. WLOS, all the friction losses, through all the pipes and all those equivalent lengths for fittings. WOS, all the pressure needed to overcome any elevation rise from the pump up to that sprinkler. It's this big cumulative calculation that tells you exactly how strong that pump needs to be.
Can you maybe walk us through a scenario, a real-world example where getting these calculations right or wrong makes a huge difference?
Sure, let's take a common one. Imagine you're designing a sprinkler system for, say, an ordinary hazard occupancy, maybe a light manufacturing plant, something like that. Your first step is analyzing the layout, the hazard. You identify the remote area. Now remember, that's the spot that's hydraulically most demanding. Not always the physically furthest point, but the area where the water has the toughest journey, most friction, most elevation lift, maybe smaller pipes feeding it. Okay, let's say this remote area needs 12 sprinklers to cover it properly according to NFPA 13. Your initial calculations, using QK for each head, show that each of those 12 sprinklers needs to discharge, let's say, 22.6 GPM. So 12 heads times 22.6 GPM each. That's 271.2 GPM just for the sprinklers operating in that specific design area.
Okay, 271 GPM just for the sprinklers, but that's not the total water needed from the source, right? The pipes themselves need water too.
Exactly. And this is where it gets really interesting, and sometimes where less experienced designers can get tripped up. The total water demand isn't just adding up the sprinkler flows. The system also needs extra water. Flow to fill the riser, the main pipes, the cross mains, the branch lines leading to the sprinklers. Sometimes you need to add water for fire hoses too, a hose stream allowance. Let's say for this example, all that extra water adds up to another 64.3 GPM. So your 271.2 for sprinklers plus 64.3 for everything else. Your total system demand at the source is 335.5 GPM. Okay, now imagine a mistake happens in the friction loss calculation. Maybe someone assumed the pipe was newer, used a C factor of 120, but it's actually older pipe, maybe slightly corroded, and the real C factor should have been 100. That's a big difference in friction. Or maybe they missed adding the equivalent lengths for a few crucial valves or fittings along that path, or perhaps there was a small, maybe 5-foot elevation gain that got overlooked in the plans.
So even seemingly small errors in calculating that friction or elevation could start to add up, have a kind of ripple effect.
Precisely. A huge ripple effect. If those calculations for pressure loss through maybe hundreds of feet of pipe and dozens of fittings were off, or if that elevation change wasn't accounted for correctly, the pump that got selected based on that calculated 335.5 GPM demand, it might be significantly undersized for the actual system demand. It was chosen for one set of conditions, but the real-world system imposes a much tougher load.
And what happens then in a real fire?
Well, it's disastrous. The pump would turn on, sure, but the actual pressure and flow getting all the way out to those critical remote sprinklers, it would be far less than the required 22.6 GPM per head. That pump would essentially fail. It wouldn't deliver the performance it was specified for. It leaves that area, and potentially the whole building, vulnerable. Instead of getting the 22.6 GPM needed to control a fire, those heads might only deliver, 15 GPM, maybe less. What should be a robust suppression system effectively becomes, well, not much more than a garden hose in comparison. It's a stark example of how vital accurate calculations are. Even small mistakes can have life or death consequences.
Wow. Okay. So wrapping this all together for the engineers and MEP pros listening, what are the absolute key takeaways, the best practices to ensure this level of accuracy and safety?
Right. The core message is really about diligence. Unwavering diligence, continuous learning, and sticking strictly to the established standards. First, and most importantly, always refer to NFPA 13. It's the authority. It gets updated regularly based on research, testing, field experience. Keep up with the current edition, but don't stop there. You also need to be familiar with related NFPA standards: 14 for standpipes, 20 for pumps, 22 for tanks, 24 for private mains. They all interact. And, critically, always remember that codes often have exceptions. And local AHJs. They are allowed to modify standards for specific local conditions, so always check with your local AHJ.
And I guess technology must play a massive role now, right, compared to how this used to be done.
Oh, absolutely. It's
Right.
completely changed the game.
Yep.
So, second key practice, leverage technology. These calculations, they used to be this incredibly painstaking trial and error method done by hand. Hours, days sometimes, with calculators, slide rules, friction loss tables, just tedious. Today, it's done very easily with a computer program. Use specialized hydraulic calculation software, things like Elite Fire, Hydric HLC, AutoSpring. There's several good ones. These programs drastically reduce the chance of simple math errors. They let you iterate designs quickly, and they can perform really critical analyses like something called peaking.
Peaking, what exactly is that?
Peaking is it's a really smart analysis, especially for grid or loop systems. It checks if the remote area you picked initially is truly the most demanding spot. It seems counterintuitive, but sometimes, because of how pipes connect or change size, the physically furthest point isn't the hydraulically hardest point to serve. Peaking software automatically tests shifting the operating sprinkler area around to find the absolute worst-case scenario for pressure demand. It might run multiple calculations to confirm you found the true hydraulic peak. It ensures there's no hidden weak spot in your design.
Interesting. So use the powerful tools, definitely, but don't just blindly trust the output. You still need to understand the fundamentals.
Precisely. That's the perfect lead-in to the third key recommendation. Embrace thorough review and collaboration. Software is a fantastic tool, but it's not a replacement for sound engineering judgment. You have to take the time, meticulously review all the plans, all the calculation inputs and outputs, the manufacturer's data sheets for the equipment, and don't ever hesitate to ask questions. There's no such thing as a dumb question when safety's on the line. If you're unsure about something, get help. Talk to experienced contractors, senior colleagues, mentors, educators, the equipment manufacturer's reps, maybe even hire an independent third-party consultant for a review. Knowledge is only valuable when it's understood and applied correctly. Getting multiple eyes on a complex design, different perspectives, it almost always makes it better, safer. I remember finding a tiny half PSI discrepancy once, traced to one missed fitting. Seemed small, but could have mattered immensely.
This whole deep dive, it really just underscores the incredible level of precision needed in fire protection design. It's one of those fields where every single tiny detail, every calculation literally has life or death implications. It makes you appreciate the unseen engineering protecting us every day.
Absolutely. It boils down to this. Good, careful, meticulously executed calculations. They translate directly into reliable systems, systems that work when they absolutely have to. Conversely, mistakes in design,
Yep.
oversights, even seemingly small ones, they can lead directly to system failure during a fire, and that puts lives, property, everything at grave risk.
It really makes you think, doesn't it? Beyond just fire protection, think about that ripple effect, that demand for rigorous engineering precision. It's not just about checking a box for compliance or meeting a standard. It's about the fundamental trust and safety we engineer into our built environment, into every structure, every system. Makes you wonder what other areas of engineering, maybe where the stakes feel similarly high, could benefit from this kind of deep dive, really examining their core calculations, hidden complexities, something to ponder. Well, we certainly hope this deep dive has given you a new appreciation for the unseen power behind effective fire protection, and especially the critical role of hydraulic calculations. Join us next time for another exploration into the knowledge that matters.